Hello and welcome back to another lecture. In this lecture we're going to design a wall footing. The problem is on the board right there. It says design a wall footing to support 12-inch wide reinforced concrete, and the dead load is 20 kips, life load is 15. The bottom of the footing is to be 4 feet below the final grade. The soil unit weight is 100 pounds per cubic feet. The allowable soil pressure is QA is about 4,000 psi, and there's no appreciable sulfur content in the soil. Steel is 60,000 psi and the concrete is 3,000 psi. Okay, so here's a drawing of it and with the sketch on it. We see a dead load 20, life load 15, and all the information that was in the problem is right here with the soil bearing pressure 4,000 psi. To do this, we really have to assume the thickness of the footing right here. We gotta assume this. And the way I want to do this, let me shut this off. The way I want to do this is basically, let's go to Excel and assume a number of these. I've already done this. Let's do it together. Let me clean all this stuff out here. Clear content. Okay. So we're going to go ahead and assume the thickness of the footing. Normally when you do a wall footing, the thickness should be about 1.5 really. But it says 1 to 1.5 will be fine. So we're going to start with 1, which is 12. And then we're going to do 1.5, 18. Then go to 20 and go to 24. Try all these 4 different sizes. The next thing we're going to go ahead is calculate H. So I'm just going to move back between writing and Excel. So let's go ahead and calculate. I'm just going to calculate for this one, and then we enter the other one by itself using Excel. Let me close this off. Okay. So our D is equal basically H minus cover. And in our case, we said let's go with the 12-inch minus 3-inch cover minus half of the bar diameter. So D, it's going to come out to be 12 minus 3.5, which is going to be, so use 3.5 for both those combined. It become 8.5. And this is basically from ACI 20.5, I like 0.6, 0.6, 0.1, 0.3. You can look it up. And I'm gonna go back up onto my Excel again here. And right here, I'm just gonna go ahead and type in equal this minus 3.5, enter, and then go ahead and grab the corner and go all the way across, and that's what we're going to have for the rest of them. And then the net soil pressure was given to us as 4 ksi or 4,000 psi, and here I have a 4 ksi, so I'm going to put 4 ksi for all of them. And the footing weight, and let's calculate that. The footing weight, it's going to be, we have 12-inch sticks divided by 12 makes it a foot, time 150 pounds per cubic feet. So that would leave us 150 pounds per square foot. Now remember, this is very careful here. Let me go back to this shape here. So we assumed this being right here 12-inch. So that means right here it will be from here, that will be 3 feet, correct? And as we make this thicker, the soil becomes less on top. So the soil is going to be 36 inches, which is 3 feet, time, it was 100 pound. 100 pound per square foot, which is equal 300 pound per square foot. So the total of this become 450 pound per square foot. That is for H is equal 12. So let's go back to our Excel and make adjustment for the other ones. Now in here we have a footing weight. The footing weight is going to be basically equal this number right here divided by 12, make it a foot. I should put a parenthesis around it. And then multiply by 150. Enter. And then I grab this corner and I go along, and as you can see, the number is gonna change. Down here for the soil, you gotta be careful. The soil, it's gonna be 4 feet, so equal, parentheses open, 4 feet minus the up here, which is 12 divided by 12. Well, make it a variable. This divided by 12, close it, and multiply by 100. Enter. And then we're going to grab this corner and we're going to go across. And by the time we get to the end, it should be 200. The next thing we're going to calculate is, let me get out of here. The next thing we're going to calculate is the effective soil pressure. So the effective soil pressure is basically the remaining soil pressure is available to support the wall. That means you have to deduct the load from it. And that's going to be basically QE is equal, we had 4,000 would begin with. Then we got to take out the weight, which was basically 450. And that gave us a 3550 pound square foot. So let's go back to the Excel again. Right here we have the remaining, and what we're going to do is type in equal 4,000 minus this minus the second one also. Enter. So that gave us a 3550, and we're going to drag that across, and we end up with 3,500 for the 24 inch. Then we're going to go ahead to the width of the footing is required. Let's calculate the first one. So to calculate the width of the footing required, remember we're doing a 1 foot strip. Let me go to the PowerPoint for a quick second and come back. This was a good one right there. We're taking 1 foot strip, and that's what we're designing. And let's go back. And that's going to be dead load, which was 20, plus life load, which was 15 kips. Let's make that to a pound per kips. Convert that, and then divided by available net pressure, which came out to be right here, 3550. This will give me 9.86. Let's say 10 feet. So our area of the footing will be 10 feet squared, 10 times 1. And I'm going to go back to the Excel right now. Again, right here, the width of the footing required, it's going to be put down equal parentheses 20 plus 15 times 1000 divided by cell above, which is the net pressure, and enter. And then I'm going to drag the go all the way across. Pretty much 10 for all of them. Next, we're going to calculate the bearing pressure. QU is equal 1.2 times dead load 20 plus 1.6 times live load of 15, and then divide that by 10 feet square, and that will give us 4.8 KSF. Back to Excel, just put 4.8 all the way across here. 4.8 and go across. Okay, next we're going to go ahead calculate the depth required for a shear at a distance d from the face of the wall. Let's look at the wall, and we want to come away distance d from here. So let's call this D. They want to know what's the shear for this area is. I want to figure this out. Take a look at this. This is like a cantilever. So if I come back down here, it's basically like a cantilever. And the load is going to be shear is going to be basically the load itself, and moment is going to be WL squared divided by 2. You remember that from kindergarten, right? So we're going to go ahead and calculate the shear. VU is equal, that distance was, come back in here, we said this is going to be at 10 feet. So now I'm going to come in right here down the center, and this is going to be 6 inch right there. And then 6 inch plus D, whatever D it is, then we have this left over to us. So that's where it comes from. VU is equal 10 feet divided by 2, that would take it to the center. Take out the thickness of the wall itself, 6 inch divided by 12. And then take out the D, which was 8.5 divided by 12. And then multiply that by 4.8 kip per square foot. And that's going to give us 18.2 kip, or 18,200 pounds. Let's just round it to that number. Going back to the Excel sheet, and we're going to come in right here, calculate VU, which is equal parentheses open 5 minus, instead of 6 inch I'm just going to put a 0.5, we already know that, and then minus the D is right up here, divided by 12, close the parentheses, multiplied by 4.8, enter, and that's what it is. So let's drag this across. Hopefully they all come out good. They look all right. Next we're going to calculate the depth of D. Let's go ahead and do that. Let me go to the PowerPoint, show you where D come from. We're going to use this equation. There's an equation someplace. Right here. We're going to use this equation for D. That's per ACI. So let's go ahead and plug that equation in. Actually, it was in the spreadsheet too. So our D is equal VU divided by phi times 2 lambda square root of prime C times BW. And we're going to have 18,200. Phi is 0.75. time 2, lambda is 1, and square root of 3000, and then time 12 is our width, and that comes out to be 18.45. Now our height is going to be d plus the cover, right? So it's basically 18.45 plus 3.5, and that comes out to be 21.96 or 22. Remember, we said our assumed to be 12 inch. So this is bigger than 12 inch. Of course, it's no good. That number should be less than what we assumed. So let's go ahead, go back to the Excel. So now we have D is equal, right there, this here, put the equation there, it's up there. And then grab the corner and drag it. Then we're going to calculate H. H is basically D plus 3.5 inches. And there we have. Now, here's the thing. We selected to H be 12 inch, but in here for the shear we need 22 inches. So this is no good because it's less than 12. 19.5 is more than 18, so that's still no good. 18, 7.5, that's good. 17, that's good, less than that. So I'm going to put down right here, no good. This one is also no good. And these two are okay. Okay. And the next we're going to now we're going to basically narrow down to our, let's just work with the 20-inch thick footing. And then we're going to continue from here. We're going to calculate the steel, and then we're going to check the development length. All right, the next thing we're going to do is calculate the area of the steel, and there are a number of ways you can do it. There's a table you can use, which basically it gives you correct steel, or you can use mu divided by 4D. That's kind of high, but it will do the work. Or we can go ahead and follow the ACI, start from a minimum and work way up. Let's go use the ACI method. Let me bring this PowerPoint up, see if I can find what I'm looking for. If you look at right here, ACI, both 7.6 and 24, it says use a 0.0018 times the gross cross-sectional area to calculate the steel area, AS minimum. So let's go back to the writing. First thing we're going to go ahead and do, calculate the MU. The MU is, if we look at this right here, and we basically treat this as this area right here, right? This considered as a cantilever from face of the wall to the edge of the footing, so it's a cantilever. And we're going to calculate both MU, and we did calculate the shear. So let's go back and calculate that. If you look at the uniform distributed load for moment, maximum moment for MU is WL squared divided by 2. And look in any beam formula table will tell you that. And our W was 4.8 kip per foot. And then we have L squared is basically 4.5. What do I got? 4.5. If you look at the length from the face of the wall to the edge of the footing is 5 feet minus 6 inch. 5 feet minus 6 inch. Makes it 4.5. Then divide by 2. That should give us 48.6 kip foot. The next thing we're going to calculate is the MU divided by phi BD squared. That's 48.6. Let's convert that to an inch kip times 12 times 1000. So now it's an inch pound. The unit become inch pound. That's what we did. Phi for a beam is a 0.9, and 12 inches a B, and our D was for 20 inch was 16.5, and square that, and that will give us 198.3. The AS minimum per code is given as 0.0018 times the gross cross-sectional area, which in our case will be B times H, 0.0018 times 12 times 20, and that will give us 0.432 inch squared. Now I want you to pay attention here. This is a bare minimum. You cannot go any lower than this, so you got to make sure when you pick something, pick one or two higher. Let's go look at the table here. Okay, so if you look at the table, we had 0.432. 0.44 is number 6. That's too close. Let's go one higher. Go to 0.6. Let's pick number 7 bar. If we pick number 6, it will fail. But if you pick number 7, it will pass. Let's just pick number 6 so we say how it fails. Okay, we're going to try number 6 rebar at 8 inch spacing. This is just for exercise. This is not going to make it, but let's try it anyway. So the area of the steel per 1 foot strip is going to be, the number was 0.44 for number 6. So AS number 4 is equal 0.44, and that's from the table. So 0.44 divided by time, 12 inch. We're going to go 8 inch spacing, and that will give me a 0.66 inch square per foot section. Let's change color for good luck. And then we're going to calculate, remember A, size of the block, it's AS times FOI divided by 0.85 F prime C times B, and that gives us 0.66 times 60 KSI divided by 0.85 times 3 KSI times 12. I get 1.29. Then we're going to calculate phi times MN, which is equal phi times AS. Remember those? FOI times D minus A divided by 2. And that's basically 0.9 times 0.66 times 60 times 16.5 minus 1.29 divided by 2, and that's equal 565. That's inch kip. Remember, just make sure your unit is correct. Inch kip. We don't like inch kip. We want to make them to let's convert that to a foot kip. So if I have 565 divided by 12, that will give me 47.08 foot kip, which is less than our number was right here, 48.6 kipped. This is the load, this is capacity. I can't spell today, so it's no good. That's why I said usually you pick this rebar, go twice. So let's go back to the PowerPoint. We picked our area where we picked this one was kind of close. Let's pick number 7, which is a 0.6. So I'm going to come back and do the same exact thing, but this time I'm going to pick number 7. So I'm going to say try number 7 rebar, the AS is 0.6 inch square. So our AS per 1 foot strip is 0.6 times 12 divided by 10, and that's equal 0.72, I believe. Okay, 0.72 inch square per foot. The next thing we're going to calculate is the A, and A is going to be basically 0.72 times 60 divided by 0.85 times 3 times 12, and our A should come out to be 141. Then after that, we're going to calculate phi times MN, which is equal to 614 divided by 12. That will give us 51.2, which is bigger than 48.6, and that will pass. That's good. Now look at the Excel sheet here. So if you go back to the Excel sheet, I did it for both sides and broke it down, and the second one which was 51.2 then. So this is done. Our last check is check the development length. A lot of people don't know what development length bar is. Let's go talk about that a little bit, and then we can calculate the development. So the development length is explained in section 25.4.2. It's a lot of good reading here. The equation is given by right here. Fy is equal to these factors and divided by 25 lambda square root of f prime c times diameter of the bar, and these are for number 6 or smaller, and our was number 7, so we're going to use this one right here, divided by 20 lambda square root of f prime c times diameter of the bar. And there are other cases too, but our case is right there. So what is the development bar? It's really refer to a minimum embankment length required for reinforcement bar. So when you design your footing, you want to make sure the bar is meet both tension control and compression. It's long enough to make a bond between that and the concrete. And if your development length come out bigger than right here, from this distance to the end of the from the face of the footing to the end of the footing, I mean from face of the wall to the end of the footing, if the development bar comes out larger than this, then your footing is not large enough, so you make a bigger footing. Because this is the available right here, what I got right there, that's the available area for your length. So let's go ahead and see where ours fit in. The equation right here says LD is equal FOI times these factor, T, there's one for E, I think there's one for S, and divided by, in our case, is 20 lambda times square root f prime c. All of these comes out to become 1 because the spacing bar exceed the code says if the spacing exceeds 2 times diameter of the bar, which it does, and also for different number bar, those are different a little bit. And let's look at the specs, see what they say here. Go back to it actually. And right here is explained right there. In a commentary talks about it right there, the ACI. So our comes out all ones, so we're gonna go ahead and use 1 like they have here, and our lambda comes out 1 for 3,000 pound concrete. So let's go back to the writing. Okay, then we have 60,000 times 111 divided by 20 times 1 times square root of 3,000, and that comes out diameter of the bar. It comes out to be 54.7 diameter of the bar. Our bar was number 7 rebar, and number 7 rebar has a diameter of 0.875. So our LD is equal 54.7 times 0.875, and that will give us 48 inches. How do you like that? Okay, next we're going to compare that to available. Development length. This is our development length. It's from face of the wall to the edge of the cover. We got 3 inches of cover right here, and from the center of the wall to the edge of the wall is a 6 inch, and this whole thing is a 10 feet. So that becomes 10 feet divided by 2 minus 6 inch minus 3 inch. So I'm going to come back down here and say the available length is 10 feet divided by 2. Let's multiply that by 12, make it an inch, and then minus 6 inch and minus 3 inch. So that become 5 feet 60, 60 minus 6, 60 minus 8, it makes it 51 inch. 51 inch available. So our 48 inches less than 51. Our footing is big enough, we don't have to do anything, so that will check. The next thing we're going to go ahead and calculate, we're going to calculate the so the next thing we're going to do is calculate longitudinal temperature and shrinkage rebar perpendicular to the number 7 bar. And I think that's ACI 24.4.3.2. I showed it to you earlier on a PowerPoint, and I said the minimum area is 0.0018 times BH, which we already have done. That is 0.0018 times 12 times 20, and this is per 1 foot section. You see a lot of books, that's 0.18. A lot of books, they might use the entire length of the footing. We're just going to use the 12 inch one for per 1 foot section, and that's equal 0.43 inch square per 1 foot section. Keep that in mind. So we're going to say, okay, we're going to use number 5 at 8 inch spacing. Number 5 rebar has this area of 0.31. So if I take AS per foot, and that's equal 0.31 times 12 divided by 8, and that gave me 0.465, which is bigger than 0.43. So we're good there. And next we're going to go ahead and draw everything together. Okay, don't pick on my drawing. I didn't go to kindergarten. So here's our footing. Our footing was 20 inch thick, so the cover become 28 inch to the top of the ground because it was 4 feet from here. And then our longitudinal bar came out number 7 at 10 inches spacing at the bottom. Then we have a shrinkage bar at number 5, and then that will tie into the dowel bar for the future wall design. Hope you liked it, and have a good day.